gotta be kidding. Corey. Yep, you seem like a smart man, and I'm a lazy man, so maybe you can help me with something.
What you got?
I have to empty this entire hot tub with just this pail. There's gotta be a better way.
Well, we can put a siphon hose in there.
A water hose?
Yeah.
I just called you a smart man. You expect me to believe that I can put a water hose down and into this water, running up and over the side, and it's gonna drain.
Oh yeah? As long as where you're putting the water out of the hose is lower than where we're taking the water in, it should work.
Well, I'm not gonna take your word for it. You're gonna have to prove it to me.
Well, come over to my office. Let me show you something.
All right, Corey, what you got for me?
All right. This is our diagram for this particular instance. This is our body of water, and this is the water hose. This is point 1, which is at the inlet, and that is point 2, which is at the outlet. And the outlet, notice, is lower than the inlet.
Okay, so what's your first equation?
This first equation right here, that is Bernoulli's head form. It has the pressure, height, and velocity relating from point 1 to point 2.
Okay, and your second equation?
That is a relation of the mass flow rate that equals the density, area, and velocity flowing through the pipe.
Okay, and your third?
That's the conservation of mass, which states that whatever goes in must come out.
Okay, so what's all this down here at the bottom?
This, in our instance, is what cancels in the Bernoulli equation.
Okay.
Since we're at atmospheric pressure on both ends of the garden hose, pressures cancel, and there's no velocity at point 1, and point 2 is our reference, so it's 0. So you end up with Z1 equals your velocity at point 2 over 2g, which equals V2 equals the root of 2g Z1.
All right, so looking at this, as long as there's a height difference between point 1 and point 2, we know there's a velocity.
Yep.
And since there's a velocity, there's also a mass flow.
Correct.
And if there's a mass flow coming out at point 2, that means that at anywhere in this hose, there's going to be a mass flow?
Yeah, that's why I can go in the outlet and up and over the side.
All right, seems to make sense. In any case, can you show me how to do it?
Come around side over here. All right. This is our experiment you wanted to know about. So you see, that's our bucket, and here's our hose.
Okay.
It's running all the way to over here, and it's going to flow into that bucket, which we're going to weigh before and after so that we can get the mass flow rate. And we're choosing such a small time so that the change in height in that bucket is negligible, so we don't have to worry about that.
Sounds good. Let's get it done. All right, so once we finished our experiment, we found that our mass flow rate is 0.3 kilograms per second, which we got by taking the difference between our measured weights and the time. Then we plugged that into this equation and solved for velocity, which we found to be 1.515 meters per second. Unfortunately, whenever we solved for all of the Bernoulli's equation, we found that our V2 was supposed to be 6.314 meters per second. What's going on? Why are they different, Corey?
Well, Bernoulli's isn't exactly perfect, so we're going to have to use the energy equation that's also a branch of Bernoulli's, and it accounts for head loss.
Okay. And what is head loss dependent on?
It's dependent on the friction of the fluid going through the pipe and the length of the pipe.
All right. So, are we able to solve for HL?
Yeah, we can.
Okay, so we solved our HL using our experimental velocity, which we know is true, and it turns out that our HL is equal to 1.915 meters. So what happens if we use an even longer hose?
Well, let's go find out.
So when we did our second experiment, which is in blue marker, we found that our mass flow rate is 0.14 kilograms per second.
Are you colorblind?
It's in blue. What are you talking about?
It's green.
I don't care.
We'll continue.
All right. So our velocity came out to be 0.7 meters per second whenever we plugged it into the equation. Then, whenever we found head loss the second time, we found that our head loss was 2.01 meters, which is larger than whenever we used the shorter hose at 1.915 meters. So from this, what we can learn is that if you're going to siphon, which is completely possible, you should use the shortest possible hose with the least amount of friction so that it happens with the least amount of head loss.
Correct.
Well, Corey, this has been a wonderful learning experiment, but it's almost dark and my hot tub's still full. So,
Better get to siphoning.
all right.